So, have you had a break? Hope you have. In this video, we're going to continue with our discussions of the postulates of quantum mechanics. In the last video, we looked at postulates 1 and 2. In this video, we'll look at postulates 3 and beyond. So, what is postulate 3? Postulate 2 told us that for every observable, for everything we could measure in the lab, there was a corresponding quantum mechanical operator. Postulate 3 gives us an idea about what this means. So, in postulate 3, we're going to introduce what's called operator algebra. And basically, what this represents is what happens when we operate on a mathematical function with one of these operators. What's important in quantum mechanics is what we call eigenvalue equations. All right. So, for example, if we take an operator which we will designate here as O, capital O, with again the little operator hat on top of it, and we're going to operate on our wave function psi. Okay, and the key is if, all right, we get a constant represented by the little o times our original function. All right. So a constant times our original function, then we have what's called an eigenvalue equation. All right. So again, if we get an operator operating on our wave function psi, and we end up with a constant times the original function psi, we have this eigenvalue equation, and the constant is referred to as an eigenvalue. The function psi is referred to as an eigenfunction. Now, it's important to note that operating on a function does not necessarily give us a constant times the original function, and we'll look at an example of that in a little bit. If it does give us a constant times the original function, then we have this eigenvalue equation, and that constant is an eigenvalue. Alright, so let's take a look at the situation here with momentum. So here's our momentum operator operating on psi. You may recall that our momentum operator was h bar over I, and it had the derivative here associated with it. So when we operate on psi, we're just going to take the derivative of psi with respect to x. So if we operate on our wave function and we get a constant times our original function, then c is the constant here, is the eigenvalue. And what that means physically is if we have our system in a state represented by the wave function psi, we go into the lab and we try to measure momentum in the x direction. This means that the eigenvalue is the only possible result we can get. So the eigenvalue tells us what we're going to get when we measure this in the lab. Okay? So let's consider the situation where we had the free particle in space. If you go back, you'll remember that the wave function for that free particle was e to the ikx. Well, let's ask the question, suppose I want to measure the momentum of that free particle. What am I going to get? Well, in order to determine that, we take our momentum and we operate on the wave function psi. And when we do that, we'll note that we're taking the derivative of e to the ikx. Oops, I didn't mean to do that. E to the ikx. Okay? And you go back and you look at the derivatives, you'll find that the derivative of e to the ikx is ik times e to the ikx. Alright? Which we can multiply things out. We can see that the i's cancel out very nicely because we don't want to have an imaginary result. And we get h bar times k times e to the ikx. Well, what we have here is k and h bar are both constants. So we have a constant times our original function, e to the I kx. So that means that our function here is an eigenfunction of the momentum operator, and kh bar is the eigenvalue corresponding to that function. And because kh bar is the eigenvalue, that means that is what we're going to measure in the lab. Let me just repeat that. kh bar, being the eigenvalue, is going to be the result and the only possible result of a momentum measurement of this free particle in the lab. All right. Now, another example of an eigenvalue equation is the Schrödinger equation, because you recall that Schrödinger equation had the Hamiltonian operator operating on the wave function psi, and it gives us E times psi, where E is the energy and is a constant. So the energy E is the eigenvalue. So if we have a wave function that's an eigenvalue of the Hamiltonian operator, that means that if we measure the energy of the particle in the lab, then the value we're going to get is E, and that's the only value we're going to get. Okay, so these are examples of cases where we have eigenvalue equations that tell us what we're going to measure in the lab, and very specifically what we're going to measure in the lab. Okay. All right, so let's go on to postulate 4. Okay, postulate 4 has to do with a series of measurements that we make in the lab, and basically what is the average value associated with those measurements. All right. So, for example, if our function is not an eigenfunction of a particular operator, what does that mean? Now, we just learned that if a function is an eigenfunction, it means we get an eigenvalue, and the eigenvalue is what we're going to measure in the lab. But what if it's not? That means if our state is represented by a function that's not an eigenfunction of a particular operator, there's more than one possible outcome to a series of measurements that we make in the lab. And you know that if we have more than one possible outcome, that means we have to find out what the average is. So let's look at an example. The one-dimensional box. All right. In that case, if we're again looking at momentum in the x direction for that one-dimensional box, just like we did on the previous slide with the free particle, okay, we're going to take the derivative of our wave function. And when we take the derivative of our wave function, here's our wave function for the particle in a box. It's a sine function. When we take the derivative of a sine function, we get a cosine function. Now, that means that we don't get a constant times the original function, because we started out with a sine function and we end up with a cosine function. So this wave function, the sine of n pi x over L, is not an eigenfunction of the momentum operator, because we don't get a constant times the original function. And that means that when we go into the lab, if we have a particle that is in the state described with this function, and we attempt to measure the momentum, we are going to get more than one outcome. We can expect to measure momentum, make a series of measurements, and we may get different results for each measurement. So again, in that case, we know we have to know, okay, I know I'm going to get more than one. I have to then determine what my average value is. And that's where this thing called the expectation value comes into play. This is going to give us the average value. So how do we do that? Well, it's an equation that requires integration. Of course it does. All of our equations require integration. So this little goody here means, with the little brackets on either side of the O, means that this represents the average value of O, a particular property, momentum for example, and that is equal to this expression where we have an integral of psi star times an operator operating on psi, d tau, so it's integrated over all space, remember that's what that means, divided by this integral of psi. Okay, I had a little interruption there. I hope you heard that, but let me just repeat. This expression gives us the integral of psi star multiplied by the result of the operator operating on psi, integrated over all space, divided by just psi star psi, integrated over all space. Doing that computation will give us the average value of measurements in the lab. And again, right now this may seem kind of abstract. In a future video with the particle in the box, we'll be actually looking at very specific computations associated with expectation value. So you'll get some examples of this. We're just laying the foundation right now. All right, so let's just simply ask the situation. Suppose we have a case where we do have a function that is an eigenfunction of the particular operator. What's the average value going to be? Well, what should it be? If we're only going to get one measured result in the lab, that means that the average value is going to be that measured result, which is, of course, the eigenvalue. But let's just work that through. All right, so here we have the eigenfunction equation. Operator operating on psi gives us a constant times our wave function psi. So we're trying to evaluate the numerator here. Okay, so let's go ahead and do that. We know that operating on psi gives us O times psi, O being the constant. So we just substitute that into our integral. So we now have O times psi, O again being the constant there. And because it's a constant, we can pull that outside of our integral. So we end up with O, the eigenvalue, times psi star psi d tau. Okay? So there's our numerator. Our denominator, of course, is psi star psi d tau. So we'll notice that those two cancel out, and the average value is equal to the eigenvalue. And of course, as I mentioned earlier, that should make complete sense to you. If there's only one possible result in the lab, let's say our eigenvalue is equal to 1, then every time we go in the lab, we're going to measure 1. So 1, 1, 1, 1, 1. Let's say we got 4 measurements. They're all equal to 1. The average value, of course, is equal to 1. And that's the case because, again, the eigenvalue is the only possible outcome to the measurement. All right, that's the big deal here. The eigenvalue is the only possible outcome, and therefore, if it is an eigenfunction, we're only going to get one result. Again, if it's not an eigenfunction, we'll get multiple results, and that's where we have to use this expectation value equation for multiple results. And again, we'll be looking at specific examples in future videos. Okay, so what does quantum mechanics boil down to? If we're using most of our computations, we're just going to be dealing with the time-independent Schrödinger equation. So, we have h psi is equal to e psi, so we have, as mentioned earlier, an eigenvalue equation. And E is psi is the eigenfunction of the Hamiltonian operator, and E is the eigenvalue. Psi, the wave function, is referred to in this case as a stationary state because there's no time dependence associated with it. And basically the objectives of quantum mechanics are when we have a particular model, atom, molecule, whatever, we first have to figure out what the Hamiltonian operator is for that particular system. Then we solve the Schrödinger equation, which is a differential equation. And then we find the wave functions, which are the eigenfunctions of that Schrödinger equation, and the corresponding energies. Those basically are the objectives of our computations. So we're looking at, as chemists, molecules, and we'll be doing this for molecules. And we'll be doing using some pretty sophisticated computational software to do it, but that's basically what these programs do. They figure out the Schrödinger equation, they find the wave functions which represent states of the system, and the corresponding energies. All right. So finally, postulate 5 is just a time-dependent Schrödinger equation, and just very simply, what this does is it gives us the time evolution of our system. You'll notice we have a derivative with respect to time here, so it tells us how our wave function changes with time. That's what the derivative does. This again is our Hamiltonian. And again, the capital psi just represents the time-dependent wave function as opposed to the time-independent wave function, which again, for the most part, that's all we're going to be using this semester. Okay, so those are our 5 postulates. In our next video, we'll go back and take a look at the one-dimensional particle in a box and explore, using these postulates, the meaning of the results in more detail. See you then.